I would like to present you some ongoing work with Shibashis Guha, Ismaël, Jecker and Karoliina Lehtinen on Parikh automata. So let's begin by briefly introducing the model. So we have a Parikh automaton here. It looks a bit like a standard NFA. We just have vectors of natural numbers labeling transitions. And we have this set C, also containing vectors of natural numbers, all of the same lengths. And the set C has to be semilinear, so definable by a formula of Pressburg arithmetic. Okay, so how does such an automaton work? If you have a run of the automaton, it processes a word as usual, but we also can compute a vector from such a run by summing up all the vectors that label the transitions, okay? And then this run is accepting if it ends in an accepting state, and if this the sum of all the vectors labeling the transitions is in the semilinear set C. So for example, in the automaton up there, we count the number of A's and B's until we get to the accepting state where we stop counting, okay? So what's going on is we count the number of A's and B's in some prefix. And the semilinear set now requires that the second entry, so the number of B's, is strictly larger than the number of A's. So the language of that automaton is the words over AB, such that W has a prefix with more B's than A's, strictly more B's than A's. Okay? So this is the model we are looking at, and why are we looking at it? It's a quantitative extension of the regular languages, so that's always nice. And it has several equivalent definitions. So there's a definition via logic, via counter machines, and it has some nice properties. So emptiness is decidable, so you can do something with it. And it has some nice closure properties, but not all them. And it turned out to be quite useful in application. So you can query graph databases, you can model check certain transducer properties, and so on. So it's a nice class, but so far it has only been looked at for finite inputs. So what we now did here is we looked at Parikh automata on infinite words. We looked at games with Parikh automata winning conditions. And the reason we started this work is actually we looked at history-deterministic Parikh automata. And I want to present you some results for all three of these themes. Okay, so let's begin with Parikh automata on infinite words. Remember that in a Parikh automaton on finite words, a run is accepting if it ends in an accepting state, and if the sum of the vectors on that run is in the semilinear set. Okay, so let's say such a run, a finite run, is called accepting if these two properties are satisfied. Now we can define acceptance condition for infinite runs, and these are natural extensions of the typical runs you consider for omega regular automata. So for example, you have reachability acceptance, some run prefix is accepting, meaning that at the same time you're in an accepting state, and the sum of the vectors is in C. You can have Büchi acceptance, all run prefixes are accepting, so you're always in an accepting state and always in the set C. You can have Büchi and co-Büchi acceptance, which are defined as expected. Okay, and we looked at all these acceptance conditions. So the first theorem is a positive one. It says that emptiness is decidable for reachability and Büchi Parikh automata. So there we get the same even the same complexity as for finite words. On the other hand, as I only mentioned reachability and Büchi, you can already expect what happens next. Emptiness is unfortunately undecidable for safety and co-Büchi Parikh automata. Okay? And now, if you look closely, you notice that something is not quite right. Emptiness is decidable for Büchi automata, or for Büchi acceptance, but undecidable for safety. But in the classical setting, you can reduce safety to Büchi, right? So what's going on? It's just that this reduction is not possible for Parikh automata. It turns out reachability Parikh automata can be transformed into Büchi and co-Büchi Parikh automata, but all other models are pairwise incomparable. So in particular, you cannot transform safety automaton into Büchi automaton in this setting. And this is the reason why Büchi acceptance can be decidable, but safety acceptance can be undecidable. Okay, so for some classes we have decidability of emptiness, for others not. Okay, let's continue with games with Parikh automata winning conditions. These are defined as expected, so you have two players, like in a Gale Stewart game, producing an infinite word, and if it's in the language, then one player wins. If it's not in the language of the given automaton, then the other player wins. And since emptiness of safety automata is undecidable, this easily carries over to the undecidability of solving games. So even if your winning condition is given by a deterministic safety Parikh automaton, solving Gale Stewart games is undecidable, unfortunately. Okay, so much for games. But let's now talk about history determinism. This was the original motivation. So we wanted to look at history deterministic Parikh automata. And typically the motivation for history determinism, which is also called good for gameness, is that you want to solve games. And this is in particular interesting in settings where games are decidable if you have deterministic specification automata, but might be undecidable or infeasible when you have non-deterministic specification automata. But when we started this work, we noticed that actually games hadn't been looked at to the best of our knowledge. So we first had to solve games, and then when they were undecidable even for deterministic automata, that means that history determinism for solving games is not that interesting, but nevertheless it can be interesting because typically history deterministic automata are, because they have restricted non-determinism, they sit somewhere between deterministic and non-deterministic automata. And this is exactly what we were able to show here. So let me briefly explain what history determinism is. So look at this automaton we saw in the earlier example. You have to accept a word, you have to make a non-deterministic choice, essentially to see or add a prefix where you have more B's than A's, right? But this is non-determinism you can resolve based just on the history of your input. If you have access to the word you have processed so far, then you can determine whether you now have a prefix that has more B's than A's or not. So you don't need access to the future of the word, the whole word, to construct an accepting one. And this is exactly the definition of history determinism. The non-deterministic choice can be made based on the prefix processed so far and the next input letter, but independently of how the word continues afterwards. Okay, and this is called history determinism or good for gameness. But recently these two terms were separated for certain class of automata, so we prefer to use here the term history determinism. So it turns out that history deterministic Parikh automata are indeed more expressive than deterministic ones, but less expressive than non-deterministic ones. So they sit strictly in between the deterministic and non-deterministic Parikh automata, and have also some nice closure properties that you can exploit. So we have found a new class of quantitative automata with some nice properties that strictly extends the class of deterministic Parikh automata. Okay, So in the preprint, which will appear on the archive soon, we will study many more problems. So for example, closure properties and decision problems for Parikh automata on infinite words and history-deterministic ones. We will also present more expressiveness results there. So if you have any questions, Shibashis and Ismaël are add highlights this year, or just shoot any of us an email. Thanks.